We won't cover every section in the chapter on resistors. For example, I would exclude the section on multi-loop circuits. Those are complicated, and there's nothing really conceptually different from what we do. You should know what's called Kirchhoff's laws. That you should know what they mean, and we'll go over it. And the other thing that we will not hold you responsible for, but it's a good thing to know about, is electrical safety. The section there. Good advice is don't touch bare wires, to sum up that section. But today I would like to do a little bit more on resistors and currents, circuits, shall we say, circuits, and try to fill in some things there. And then to get into capacitors and energy, in the energy in the electric field. So I think we can get started with viewing. Okay, we have the idea that we can apply what's called an electromotive force, like a battery, which has the property of taking charges and separating them from each other. Plus and minuses somehow get separated from each other, or else are given higher energy by some source of other energy. For example, in a power plant, they burn coal, they burn gas to do some work which manages to separate charge. We'll get into that later. But by some means, electric charges separated from each other and create this electromotive, well, force. That was the word. That word comes down from historical things. People thought of it as a force. It's actually an energy measured. It's an energy per charge. So the electromotive force is really given in volts. So that's what your battery will talk about. Your battery will say on it how many volts, which is how much energy for each charge that comes out of the battery. Or if you plug into the wall, the electric company will tell you that if you plug into the wall, they will provide you, as we're going to go into this in some detail, from the power plant someplace, they will provide you eventually with 120 volts. That's 120 joules of energy for each coulomb of charge that you take. But they promise you that much voltage, that much energy for each charge that you take. And you take how much, as you'll see, you tell them, or by using it, how much current you take. So for each coulomb that you take, they'll give you 120 joules for every coulomb. So they're giving you energy. We'll go into that in some detail because I think that's really worth knowing. So that's the source of this electrical push, which is the cause of the flowing of the charge. It's the so-called electromotive force, EMF, which is like a pressure difference. Okay, and we recognize that there are a whole different range of ways of doing that. This one here, for example, is of course key. It's what keeps our civilization going. And that's what all the fighting is over. It's how do you get the energy to create the electricity? Where do you get the oil? Where do you get the gas? Where do you get the coal? To drive the power plants, to send the electricity around the world, to electrify the world. This is the basis of our civilization. How do you get this EMF? I'm sorry, let me see what I said here. Okay, now the other thing that we're talking about is we had problems earlier, examples of where we put electric charges into electric fields in a vacuum. Oh, you have one on your homework today, for example, where a charge in your homework, we put a charge over here between two plates, an electric charge, and we shot it, a negative charge, we shot toward the negative plate, and it sort of has to end up back at this plate. So those are the kinds of problems that you can do when the charge is in a vacuum, and the only force that's acting is the electric force, say, in between these plates. But I said a few times already that the other situation, which is more common to our experience, is that we try to get these charges to move through a wire. And in so doing, as in the demonstration of the nails in an inclined board, the charges are being pushed by the field, under the pressure of the field or the voltage difference, down the wire, but they bump into irregularities in the wire. If the wire were perfectly uniform and perfectly organized, the electrons actually could get through. But the problem is that in real wires, it's not like that. First of all, they aren't perfect crystals. You make a wire by actually taking, say, a piece of copper and squeezing it through a little hole and drawing it out. So you get a kind of irregular structure to begin with. And the other thing that goes on is that normally we're working at a real temperature. And when things have a temperature, the atoms are moving. So here's an electron coming along, and the atoms are moving. So it bumps into the irregularities, the irregular motion. It's sort of like running through an orchard. Suppose the trees were very, very well aligned in rows in an orchard. You could run very swiftly through that orchard between the trees because you know where they all are. On the other hand, if it's a forest, you can't run in a straight line. It's irregular. So that's one thing. And the other thing is the wind may be blowing. So as you're running, the branches get in your way. That's the heat motion, which is the wind, by analogy. So you get, you'll see the one little thing I want you to realize generally about resistance, or actually resistivity, I maybe mention it, is that typically there are two effects going on. One is that there's a temperature effect. So at high enough temperature, the temperature can do something to you. But at low enough temperature, other things will come in, namely the irregularities. So your typical resistor will vary with temperature, something like this. This is called the residual resistance, which is due to sort of static impurities or irregularities. For example, there might be a little crystal like that, and another one like that, and so on. When the electron reaches the boundary, it sort of has to reorient, and so it scatters. That's this kind of thing. So it's independent of temperature. It's due to the sort of irregular structure, the static structure. And then you have an effect here due to temperature, the heat motion of the atoms. So this is all I really care for you to know at this point about how a resistor would vary with temperature. It's pretty logical. And And that has to do with this opposition to the flow, which is the clogginess of the thing. There are two features here, that there's a certain basic stuff which has sort of regular positions, but even with that, the positions could change, which affect the clogginess of the pipe, and that we call the resistance here. And I showed you that. And we define resistance as it increases it is a property of the material. It may depend on temperature, but what you want to be careful to understand that it is basically a rigid property of the material, and what you vary is the voltage, the pressure you put on it, which will result in how much current you put through. In other words, if I have a voltage across this, here's a wire or a resistor, and I put a battery here, the battery puts out a certain voltage, and depending what the resistance is, it will determine how much current flows. So a good way of putting it basically is that the current will be proportional to the voltage, the pressure you put on, but inversely as the resistance. And this is the one that is determined by the material that you put in the line, and V is the voltage from this EMF source that's pushing the electrons through there. So again, it's one of those things where you have to know what's fixed and what's varying. What is fixed and what can you vary? You can vary the voltage. You can put two batteries in. And if you put in two batteries, you'll double the voltage. The resistance is the same. You'll double the current. If the material is what's called ohmic. That is, if the resistance doesn't depend on how much current you put through, which is all we're going to worry about right now. So we have that. Then we have the idea of resistors in series and parallel, which I started to show you the demo there. Now, the thing that you want to understand as a general principle is, oh, by the way, does everybody notice this, that we're going to exclude those two sections, right? You all heard that, so I can erase it? Except that these so-called Kirchhoff laws you should know because they're very general. Okay. The thing that you should know simply is a very obvious thing. That is that if you have objects in series, it doesn't really matter what they are. If this is a series connection to a source of some sort, it could be any kind of a source. Whatever current flows in here must flow out here, must flow out here, so the current is the same throughout. That's a basic idea. It's just that the current has no place else to go. It comes in one end, it's got to come out the other. The electrons repel each other. If one comes in, one will go out. And the way it works actually is though this were a full pipe of water. If you pump water in this end, that same piece of water does not immediately come out the other side. What it does, it pushes, and the water that was here goes here. So what happens, the electron pushed in here pushes everybody at the speed of light. It sends a signal. I'm coming in, everybody else moves one, and you move through there. That's the way it would work. Right? That's pretty straightforward. But the current is the same all in series. Series alignment. As distinct from, if the objects were in parallel, this is 1 and 2, they could be different. Now, this is a little bit trickier. What you have here is, see, there's no potential difference on a wire because it's a very good conductor. So whatever V is here, is here, is here, is here. A wire is an equipotential. So if there's a plus V here, there'll be a plus V here, plus V here, because they're all on the electrical conductor equipotential. Likewise, if you have a negative here, it's the same potential everywhere, but it's an equipotential here and here. So across here, objects in parallel, the voltage is the same in all for objects in parallel. Okay? That's a very basic idea. So in order to do circuit problems, we usually try to boil it down to a single resistor and a single battery or source. In other words, we can start out, for example, in this case here, with 3 resistors in series. And what we're trying to do, if you want to find the current in the whole circuit, if you can boil it down to 1 resistor in the circuit, you just apply Ohm's law. If you can just get it down to this, well, that one I can do. You and I can do that. This is sort of what we call the equivalent resistor, or the one resistor which represents the whole circuit. So the trick that we should know is how do you start with a bunch of resistors and boil it down to 1, and then we just apply this law, and you can find the current in the whole circuit, if that's what you want to know. Or you can break it down into parts of the circuit and find current in various parts. So very easily, we can find that if you have resistors in series, this case here, that the one thing we know is that the currents are the same. I going into resistor 1 is equal to I going into resistor 2, right, and out through the circuit. So, and then we also know that the voltage difference across here is going to be the same as the voltage difference across here because they are equipotentials. So if we have an EMF here, we can say that the change in potential across each of these objects, V on 1 and V on 2, must add up because you see we're going from here to here plus from here to here. What you have is that E, the EMF, well, minus these voltage drops equals 0. Now, what is happening here? Somebody asked the question, you did, the very good question. What is actually going on here? What's going on is that this source, the electromotive source, is providing energy to the charges. When they pass through a resistor, they lose energy in the resistor. They lose energy equal to the voltage, we call it the voltage drop. You have a certain number of coulombs per second current. And the resistance has units, R is equal to V over I. That's joules per coulomb, and current is coulombs per second. So if you multiply these two together, you get joules per coulomb seconds. The coulomb seconds come out. The point is that when the current passes through the resistor, it loses its energy to the resistor. There's a voltage drop on the resistor. You'll hear engineers talk about the voltage drop, or the IR drop across a resistor, which is saying the electrons have been given energy, they come to the resistor, they push through the resistor, but in so doing they lose some of their energy. To what? They end up heating the resistor. So the resistors get warm. It's like that ball rolling down the nail thing. When the ball has some potential energy, if it rolls, it picks up speed, it loses potential, gains kinetic, but then it hits the nail, and it shakes the nail, and loses some of its speed. So it shakes the nail, it's given some heat energy to the nail, which eventually goes into the board. So eventually, we wouldn't measure it, really, it's too small, but the board warms up. So some of that potential energy is transferred from the rolling ball through the nail into the board, and the nail slows down, so it gives up its energy in coming through the resistor. So this is an energy loss. The total energy loss is IR. This is the number of, let's see. Let me see, make sure we got this right. V equals IR. R is in units, joules per coulomb, coulomb per second. I think there's joules per coulomb, coulomb per second. So there is, yeah, so the units here are joules per coulomb in a volt. So, so the point is the current is coulombs per second, and the resistance is joules per coulomb, coulomb per second. Seconds cancel. One of the coulombs cancel. So the energy loss is IR is joules per coulomb. So that tells you how much, this IR tells you how many joules for each coulomb that passes through the resistor. So that's what's going on there. And the other issue that you want to see is the idea of the power loss. And that is the energy per second. So we can get, let's see here. If we have IR, this is the joules per coulomb. If we multiply it by the current, this is coulombs per second. What we get is the joules per second. So the power is the product of I squared times R. That's a very important formula as well. So if you have a resistor, that's my blackboard here. It's true of every resistor. If you have a resistor and a current passes through it, you'll get a voltage loss, an energy loss per coulomb of IR. This is your voltage drop. And you will have a power loss. That's energy per second, which is equal to I squared R. So you'll sometimes hear engineers talk about the I squared R losses. This is a power. It's energy per second. This is very often you worry about the losses in the wires. Now, in an ordinary wire, in our type of thing, we won't worry about the power loss in these wires. Where this gets to be important is if you have a power plant and you have to transmit power over many miles. So you're passing current through a wire, and the wires are extremely long, miles long. Then I squared R in the wires. Then it gets to be important. In fact, I think the figure is that about 10% of the electricity generated, electric power that's generated in America, 10% of it is just lost in the wires carrying the power from the power plant to where it's used. That's a lot. When you figure how many gajillion amounts of fuel are burned, 10% of it just goes into heating up the wires. We'll see how you can do pretty well with that, but not perfectly. In any case, that's a little bit of a sidelight to this issue here. The point is that we can derive the equivalent resistance of a circuit like this by saying that we want to have that equal to the voltage I times an equivalent resistance, but E is equal to the V on object 1 is I times R1. Let's see. Let me do it this way. Let me say that E is equal to, I hate to bore you with this because it's an easy derivation. So if I can put the V's on the other side over here, now V1 is I R1, and this is V2 by our general rule is I R2, and the currents, because it's a series circuit, the currents are the same in both, so I divide it, take them out, and I get R1 plus R2.